Hello and welcome to this video lesson on measuring enthalpy changes, which is the subject of a required practical, the second one that you'll have done in year one of your A-level. And so this video will help you do that practical, and it will also help you do the questions on that practical that you'll get in your exam. It has specification reference 3.1.4.2. So here are our lesson objectives. Firstly, we need to know how to measure an enthalpy change. As you know, it's a practical, so we'll be measuring an enthalpy change. And we also need to know that the heat change, which we call Q, in a reaction is given by Q equals mc delta T. So we'll explain what each of those terms mean and how to use that equation, which is in fact the subject of the third learning objective. We want to be able to use Q equals mc delta T in calculations, such as calculating the molar enthalpy change for a reaction. Okay, so let's crack on. Measuring an enthalpy change in the lab. Okay, so let's just remind ourselves what an enthalpy change is. And what I'm going to do is I'm going to use a rectangle like this to represent the energy. And what I'm going to try and do is draw two rectangles that are the same size. Like this. Okay, so they're supposed to be rectangles, so they're supposed to be the same size. And let's say this one represents the energy in the reactants, and this one represents the energy in the products. So the total energy in the reactants and products is staying the same because we're not creating energy, we're not destroying energy, but we are transferring it from one form to another. Okay, so let's say it's an exothermic reaction. Okay, so we're going to have this red part of the first rectangle. So the red part represents the just draw this. The red part represents the chemical potential energy, or the enthalpy. Chemical potential energy. And let's draw in blue the kinetic energy. Alright, so the blue is the kinetic energy. Okay, so what happens is we have a reaction, and it might be a formation reaction, it might be a combustion reaction, it might be a reaction in solution. And we've said it's an exothermic reaction, so what that means is that there is less chemical potential energy in the bonds of the products compared to the reactants. So we've represented that change by a smaller red part of the box. But as you know, the total energy is the same. We've not created or lost or destroyed any energy, which means that the kinetic energy of the products is higher than the kinetic energy of the reactants, and that manifests itself as a higher temperature. So just going to write down a reminder that this is an exothermic reaction. Okay, so it's an exothermic reaction, and that's what happens with regard to the energy transfers during an exothermic reaction. And what we want to do is we want to measure the enthalpy change. So in red, what I'm going to do is I'm going to draw a line from there to there, because that is the enthalpy change, delta H. Okay, so that's what we're trying to measure. But how can we measure the chemical potential energy in a bunch of bonds in a reaction mixture? It's pretty difficult. We can't, in fact, accurately. And so what we do instead is we measure the kinetic energy change. So the kinetic energy change, if I just draw a little blue dot along there, the kinetic energy change is the same as the enthalpy change. So that has increased. So delta kinetic energy. Okay, so if we say that the change in kinetic energy is the same as the change in enthalpy, if we work out the change in kinetic energy, then we will have the change in enthalpy. All right, so that's what we're going to do in the lab. And the way that we do that in the lab varies on what type of reaction you are dealing with. And in GCSE, you will have done simple experiments to find out whether reactions are exothermic or endothermic, and you may well have used a setup like this, where you've got a polystyrene beaker, and you add two reactants, perhaps an alkali and an acid, and you take their temperature before you've added them together, and then you add them together, they react, it's a neutralization reaction, and then you take the temperature afterwards, and if it was a neutralization reaction, you'd find that the temperature would have gone up. You record that temperature and notice that the temperature of the product is higher, and so you decide that that's an exothermic reaction. And that's the sort of setup we can do in the lab here as well, except what we would do is we would quantify the changes such that from the change in temperature we could then work out the change in kinetic energy, and from the change in kinetic energy we can work out the enthalpy change. And so that's what we're going to do in the required practical. But what we're going to do is we're going to consider the different types of reaction that we can measure the enthalpy change for, i.e. solution reactions and combustion reactions. So let's have a look at combustion reactions first. And first of all, I'm going to show you a diagram of a bit of equipment that you might use if you had an industry lab. So here we've got a calorimeter on the right hand side, and you see it's a cross section, but you can imagine that it encloses your fuel. So there's a little bottle of fuel there, and the air can come in the bottom to provide the oxygen for the fuel to burn. And the fuel burns, and it's enclosed like that so we don't lose too much heat to the atmosphere, because we want all the heat to go into the solution that we're heating up. In this case, it's the water, and water we're heating up. So we burn the fuel, we heat the water, and then this thermometer is going to measure the increase in temperature of the water, and we know how much water we've got, so we know how much it's increased, how much water we've heated up, and so we can work out the increase in kinetic energy there. And just so that our temperature is correct, we use a stirrer to stir the water so that we get an average temperature. Okay, so that's a diagram of the apparatus we might use in an industrial setup. It's a bit more advanced than the one we're going to use in the school lab. But if you were in industry and doing such a practical, what your actual equipment would look like would look something like this. So this is just a real representation of the diagram we have, and our calorimeter. Well, the whole thing is the calorimeter, but this is our chamber that we put our water into. And what we can't see that I'll try and draw on is a little opening in the bottom. So that would represent this opening here on our diagram, into which we would put our fuel that we're going to burn. And what we have here is our thermometer. And this here is our stirrer. Right, and you pop this lid on the top, it would be filled with water, a known quantity of water, and put the lid on. This is just the lid here. You'd put the lid on, you'd burn some fuel, you'd take the mass of the fuel before and after, so you'd know how much mass of fuel you've burnt, and then you would take the temperature of the water to find out how much burning that particular mass of fuel has raised the temperature of the water by, and then you'd be able to work out the enthalpy change for the combustion of whatever fuel it is that you're burning. So it's the fuel that you're burning, that's the enthalpy change of combustion that we're measuring in this practical. Okay, so that's that. Let's move on and have a look at the maths. And that involves the enthalpy change equation. So let me write it out in big bold letters for you. So we've got the enthalpy change equation is Q equals mc delta T. Q equals mc delta T. So what I will do now is I will define each of the terms. Okay, so first of all, Q. Q is the heat lost or gained, depending on whether it's exothermic or endothermic, and that's measured in joules. So it's the heat lost or gained, and we measured that in joules. And this is equivalent to the enthalpy change, so I'll just summarize that by saying enthalpy change, right, but only if pressure is constant. Okay, and in our lab pressure is going to be constant because the pressure is the pressure of the air in the lab that we're all breathing, and that's pretty much constant. At least if it's not constant, that's a much smaller error than the other errors that we're dealing with here. Okay, so Q is our heat lost or gained, and that's our enthalpy change. So let's have a look at mass. Okay, so a mass of what? Well, and this is what some students get confused with. So the mass in this equation is the mass of the solution that we're heating up, right? Usually water. So I'm going to call it solution. It's usually water. Mass of the solution in the polystyrene beaker from the previous slide. Right, so it's the mass of the solution that we are changing the temperature of. Okay, so if it's a combustion reaction, obviously the temperature is going to increase, the temperature of the water is going to increase. But if it's an endothermic reaction in solution, the temperature of the water is going to decrease. So that's why I've said which changing the temperature of. So that's the mass of the solution that we're changing the temperature of. And C from physics, C is the specific heat capacity. So this is the specific heat capacity. So from your physics, you'll probably remember that that is just the amount of heat that is required to heat something up by 1 degree Kelvin, and your heat is the amount of heat required to heat 1 gram of it by 1 degree Kelvin. And so if it is indeed water, then the specific heat capacity of water is 4.18 joules per gram per Kelvin. So joules per gram per Kelvin. So all that means is that when you burn some fuel, you're going to heat some water. So for every gram of the water that you're heating up, it's going to take 4.18 joules to heat that 1 gram of water by 1 degree Kelvin. So that's the specific heat capacity, and the last term is the change in temperature. And so delta T is just the change in temperature, and it's the change in temperature of the water. I should put solution really, because it's not always water. I think you will use water, but it's the change in temperature of the solution. So, for example, if it's a enthalpy change of a reaction that we're doing, like with an acid and an alkali, it's not water that we're using, it's whatever acid and whatever alkali. But because the acids and alkalis are mostly water, we will probably use the specific heat capacity of water anyway. So this is the change of temperature of the water or the solution in Kelvin. Okay, so that's our enthalpy change equation, and what we're going to do now is we're going to have a look at using that enthalpy change equation to work out the standard enthalpy change of combustion to start with. And the standard enthalpy change of combustion we can write in short form as, so it's combustion and it's standard enthalpy change, so we're going to write it like that. And there's 3 steps to this process. You're going to do an experiment like the one we've described, and then what you're going to do is going to use the data that you've accumulated in that experiment. And the first thing you're going to do with that data is you're going to calculate the heat lost or gained during the combustion, right, using Q equals MC delta T. Okay, so you will have, let's say you've burnt some glucose and you've heated up a few grams of water, right? So you've known how much water that you've used. You know C is 4.18, and you've taken the temperature of the water that you've heated up, and so you can work out delta T. So you've got your 3 terms there from your experiment, and you multiply out those 3 terms to find your heat lost or gained. But as you know from the previous slide, this is in joules. Yes, but the standard enthalpy change, right, is measured in kilojoules. So what you're going to do is you're going to change the units into kilojoules after you've worked out what the number of joules is. So quite simple, but you need to remember that. And that's so that's our first step in a bit. Right, we're using Q equals MC delta T to work out how much heat we got out of the fuel that we burnt, and then converting that into kilojoules from joules. Okay, so our second step is to calculate the number of moles of fuel that caused this enthalpy change. So we burnt some fuel and you measured the mass of that fuel. So remember you had a little bit of, you had this little container with some fuel in the bottom, and we burnt it, and as it burned it heated up the water in the calorimeter. And so what you've got is you've got a mass at the start and you've got a mass at the finish, and then one take the other gives you the amount, that gives you the mass that you've actually burnt. So what we want is not the mass of the fuel that we've burnt, but the moles of the fuel that we've burnt. And that is a simple calculation like the ones we did in the previous section. And so we use our familiar equation where N equals the number of moles, and that's going to be mass divided by the relative molecular mass of the fuel. And what I want to do at this stage is just remind you all that this mass and this mass, right, are not the same. Okay, because that's a frequent mistake that's made. They're not the same mass. The first mass, all right, so this is the mass of, let's call it the water, and this is the mass of the fuel. So as long as you don't make that mistake, you're going to be fine. So there we are, we calculate the number of moles of fuel that caused this enthalpy change, that caused the increase in temperature of the water in the calorimeter. That's our second step. And then what we need to do is calculate the standard enthalpy change of combustion. You'll remember from the definitions of standard enthalpy changes that we are dealing with 1 mole. So this is a combustion reaction, and so what we want with our standard enthalpy change of combustion of the fuel is how much energy is given off from burning 1 mole of it. All right, so this number of moles that we've calculated in number 2 is not going to be 1 mole. It's very unlikely to be 1 mole. It can be anything but 1 mole. But we want the standard enthalpy change of burning 1 mole of it for step 3. And so that is provided by the following equation. So we've got our enthalpy change of combustion, standard pressure. Okay, so that is going to be our Q from step number 1 divided by our N from step number 2. So for example, let's say if you got, I'll put an example in, let's say your Q was 500 kilojoules, all right, then, and you burnt half a mole of fuel, then your standard enthalpy change of combustion would be 1,000, and our units are going to be kilojoules per mole. Okay, so that is our 3 steps to calculate the standard enthalpy change of combustion. It's a very frequent exam question, all right, so we're going to do plenty of practice. And the first bit of practice comes up next. So here's our question, our exam question, and it reads, in a laboratory experiment, 1.16 grams of an organic liquid fuel was completely burned in oxygen. The heat formed during the combustion raised the temperature of 100 grams of water from 295.3 to 357.8 Kelvin. Calculate the standard enthalpy of combustion of the fuel, and it gives us relative atomic mass of 58. Okay, so first things, let's just make sure we understand what the question is asking us. So let's refer to our calorimeter diagram. So it says, first of all, let's in red, let's underline all the information that we've got in the question. So we've got 1.16 grams of fuel. So that's 1.16 grams of fuel that we are burning. And we're raising the temperature of 100 grams of water. All right, so there's 100 grams of water. And we're raising the temperature from 295.3 up to 357.8. So one take the other. Let's I like to take the first temperature minus the second temperature, because that's the reason why will become clear in a minute. So if we take 295.3 and from that take 357.8, we're going to get minus 62.5 Kelvin. So that's a temperature increase, but it says a negative number for reasons that will become apparent. So we're asked to find the delta HC, the standard enthalpy change of combustion of that fuel, and it's kindly given us the MR of that fuel as 58. Okay, so that's our information. Let's refer again to our 3 steps. That's our 3 steps to help us get to the standard enthalpy change of combustion. So let's go through those 3 steps first. So firstly, we're going to calculate the heat gained in this case. So the heat gained is going to be Q, step 1, Q equals mc delta T. So mass, so which mass is this? It's the mass of the water, because it's, okay, so we've got 100 grams. We've got 100 grams times the specific heat capacity. If you remember, so it's water we're heating up, so it's 4.18. And then we've got the temperature difference. And I like taking the first temperature, the initial temperature, okay, so multiply that all through and you're going to come out with minus 26,125, and you remember the the units in this case are joules. Okay, so that's step number 1 complete. Okay, so step number 2 is to calculate the number of moles of fuel that caused this temperature increase. Okay, so moles of fuel is N equals the mass divided by the MR, but in this case it's the mass of the fuel. Okay, so the mass of the fuel is 1.16 grams, and the MR we've been given as 58. So that works out at 0.02, but we want to use 3 significant figures. So let's write it as that. So we've got 0.0200 moles of fuel. So that's step number 2 done. Now we just have to work out the standard enthalpy change of combustion. So if it took 0.02 moles of fuel to heat the water up by 26,125 joules, how much energy do we get from burning 1 mole of fuel? But just before we do that, I forgot to do this step of step 1. Okay, so we're just going to go back to step 1, and we're going to convert our joules into kilojoules. Okay, so kilojoules is going to be 26.125 kilojoules. Okay, so now we can use the kilojoules number in our 3rd step. So we're calculating the standard enthalpy change of combustion, i.e. How much energy we get from burning 1 mole of the fuel. So our standard enthalpy change of combustion, you remember, is Q divided by N, where Q is in kilojoules. Okay, so we're going to put minus 26.125 as the numerator, and we have number of moles as 0.0200. Alright, and so that comes out at minus 1310 kilojoules per mole, which is our answer in the correct units. And also, just change colour to green. Negative means exothermic, which is fairly obvious for a combustion reaction, and that turning out to be negative arises because we took the temperatures in this order. We took the final temperature away from the initial temperature, like that. Okay, so there's our answer, and that's very similar to all the exam questions you'll get on this topic. So what we just saw was working out the standard enthalpy change of a combustion reaction, but we could also have enthalpy changes for reactions that happen in solution. And 3 general types: we can have neutralization reactions, we can have dissolution reactions, such as salt dissolving in water, or displacement reactions, when one reactive metal displaces a less reactive metal from its compound. What we're going to do now is a neutralization reaction, and this would be the subject of the practical as well. So we're going to measure the enthalpy change of neutralization. First of all, let's just remind ourselves of the definition of enthalpy change of neutralization. And what it is the energy change when 1 mole of water is formed from the reaction of an acid and an alkali. So there's the key. The key is that it's the energy given out usually when 1 mole of water is formed. So water will be a product of that reaction. You'll remember that acid plus alkali gives a salt plus water. So water is the product, and what we want is 1 mole of water and the energy associated with the formation of that 1 mole of water. So that's what we're going to measure, and we might measure it with some equipment that looks like this that you'd be familiar with from an earlier slide. We've got a polystyrene beaker, and you would start with a known quantity of acid, say, and you would start with a known quantity and temperature of acid, and then you'd add to that a known quantity of alkali, and you would stir the reaction mixture with the thermometer, and you would measure the starting and finishing temperatures, and you would assume that there's very little heat lost to the atmosphere if it's an exothermic reaction like it is in this case. If it's an endothermic reaction, you'd assume very little heat is taken by the solution from the atmosphere through the polystyrene beaker, because polystyrene is a good insulator. So let's have a look at the example. Here it is. I'll read it out for you. So 50 cm cubed of 1 molar sodium hydroxide was added to 50 cm cubed of 1 molar hydrochloric acid. The temperature rose by 6.9 degrees Celsius. So we're to calculate the enthalpy change of neutralization for this reaction. And it gives us the equation for the reaction. HCl plus NaOH gives us NaCl plus water. Okay, so there's our question. Fairly straightforward, but let's, for convenience, list out our 3 steps. There they are. And step number 1, of course, is to work out the heat that is gained using Q equals mc delta T. So let's write that down. Q equals mc delta T. Now, here's the question then, what is M? Well, M is the mass of the solution. So we've got 50 cm cubed of sodium hydroxide, and we've got 50 cm cubed of hydrochloric acid. Now, of course, both of them are mostly water, so we can assume that that liquid has a density of same density as water. So the density of water is 1 gram per cm cubed. You know that. If you don't, it's worth remembering, which means that the mass is going to be the density times the volume, with the density being 1 gram per cm cubed, and the volume being the 50 cm cubed of sodium hydroxide plus the 50 cm cubed of hydrochloric acid. All right, so together that's 100. So the mass is 100 grams. So we're going to put 100 in for our mass. Now C is our specific heat capacity, and C, what we're going to do there is we're going to use the specific heat capacity of water, seeing as sodium hydroxide and hydrochloric acid are mostly water. So we're going to use 4.18 again, and that's our C. So we can move on to our delta T, and in the equation we don't even have to subtract initial from final temperatures, because the question gives us the temperature rise, so it's 6.9. Okay, so we just work that through, and that comes out to be 2,884.2 joules. But this time I'm going to remember to change the units into kilojoules, because when we're calculating standard enthalpy changes, we need our units to be in kilojoules. So that's that many joules, which is also equal to, I'm going to divide by 1,000, so that's 2.8842 kilojoules. So that's our Q, and we have Q. So step number 1 done. Step number 2 is calculate the number of moles of fuel that caused this enthalpy change. Now, of course, that's for combustion really. but we still need to calculate the number of moles involved in this neutralization reaction. So in this case, why don't we change number 2 to be relevant to a neutralization reaction. So in a different color, we're going to write the number of moles of water that have been produced. Alright, so we need this amount of heat, 2.8842 kilojoules, was given off when a certain number of moles of water were produced in this neutralization reaction. So step number 2, which I'll continue with in blue, that was step number 1. So step number 2, number of moles of water that have been produced. So let's start off by looking at how many moles of acid we used. So moles of acid, we could equally do it with sodium hydroxide, but moles of acid used is going to be our concentration of the acid times the volume. And in case you don't quite remember that from the previous section, concentration equals moles over volume, so moles equals concentration times volume. They're the equations that I'm referring to there. So the moles of acid is the concentration, which was 1 molar, and the volume was 50 cm cubed, but if you remember, we use decimeters cubed in these equations, so we have to convert that into dm cubed, and that all turns out to be 0.05 moles of HCl. Now, if we know that we've got 0.05 moles of HCl, we can refer back to the balanced equation and see this 1:1 relationship between the number of moles of acid used and the number of moles of water produced. So if we're using 0.05 moles of acid, we are making 0.05 moles of water. So moles of H2O is going to be 0.05 there. And that leaves us free to start step number 3. Let's do step number 3 here in green. First of all, let's just adjust our step so we're working out the standard enthalpy change of neutralization. And you'll remember from the definition of the standard enthalpy change of neutralization that it is the energy given out when 1 mole of water is made. Now we've worked out the energy, 2.884 kilojoules, given out when 0.05 moles of water is produced. So what we need to do is convert that, or basically factor it up to find out how much energy would be produced if we made a mole of water instead of 0.05 moles of water. And we do that using Q over N, where Q was 2.8842 and N was 0.05, and what we're going to do is just work that through. So that's already in kilojoules. We've got kilojoules. 2.88 is the number of kilojoules, so that works out at 58 kilojoules per mole, and it's a temperature increase, which means it's an exothermic reaction, so we can put our negative sign in here and our negative sign in there to make it all consistent. And there is our answer. That is what we've been asked for, which is the enthalpy change of neutralization for that reaction given those concentrations and those volumes. Okay, for the sake of completeness, let's consider all three types of enthalpy changes in solution that we might come across. So let's do this as a mind map. So we've got an enthalpy change in solution. Okay, let's leave that in the middle, and the one we've just done is neutralization. Okay, and when we were working out the enthalpy change, we used enthalpy change equals Q over N, where our Q, as always, will be Q equals mc delta T, and our N for neutralization was the moles of water produced. Okay, so that was the first type. Neutralization reaction is one of the enthalpy changes in solution, and the second one is dissolution, dissolving something. So that's the second type of enthalpy change in solution that we could possibly come across. We've not got an example of this. It's very similar, but I'll just point out for the sake of clarity what we're talking about here. So the standard enthalpy change of a dissolution reaction is per mole of solid that is dissolving. Okay, so it would be the heat given out or taken in, could be either in a dissolution reaction. So it's the amount of heat given out or taken in per mole of the solid that you're dissolving in the solvent like water. So let's have a little example here. So example, you might have sodium chloride as a solid, and you're dissolving that in water to give you what it gives you, and so it would be per mole of sodium chloride. The enthalpy change given off when 1 mole of sodium chloride dissolves in water. Okay, so as we did with neutralization, let's write our enthalpy change equation down. So again, it's Q over N, and as always, our Q is from Q equals mc delta T, but in this case, our N is going to be the number of moles of solid that dissolved. So if you dissolved 0.1 of a mole of sodium chloride in some water, that would be what N is in this case. It would be 0.1. Okay, so hopefully that's clear. And our third type of solution reaction might be a displacement reaction. Might be a displacement reaction, and in this case it's going to be per mole of either of the reactants. So if, for example, you had you were dissolving some sodium as a solid in some magnesium chloride solution, the question would specify per mole of either sodium solid or per mole of magnesium chloride solution. So in this case, our delta H again is Q over N, and our Q, guess what? Q is mc delta T as usual, but our N is going to be the moles of the reactant. Not in excess. So you will either be told to work out the enthalpy change for one of the two reactants, for 1 mole of one of the two reactants, or if you're not told that, N would be the moles of the reactant that's not in excess. So if you had this reaction here between sodium and magnesium chloride, for example, usually this sodium would be the one not in excess, and so you'd work out the number of moles of sodium you added to a large amount, an excess amount of magnesium chloride solution, and that would be the value of N that you would use in your delta H equals Q over N equation. So hopefully that sets you up nicely to solve any of the questions that you might get when you're asked to work out the enthalpy changes of any of the solution reactions. So lastly, what I'd like to do is just dwell on some of the problems with calorimetry, some of the experimental problems which you're bound to be asked about in your exam. So if there's an exam question on calorimetry, it's very likely to be questions on the problems with these experiments. So let's list them out. And what we find with calorimetry experiments is that there are certain problems. There's a couple of problems that are consistent with all types of calorimetry, whether that's combustion calorimetry or flammable liquid calorimetry, or indeed neutralization reactions. So the problems with all calorimetry, first is, of course, we've got a container, and it's we've also got a temperature change happening, and so by definition the container is going to absorb some of the heat, and if the container is absorbing the heat, the water is not absorbing that heat, and therefore our temperature increase is less than, temperature increase of the water is less than it would be if no heat was being absorbed by the container. So that's one of the problems, and so obviously you want to use a container that absorbs less heat than another one that might absorb more heat. And of course you're always going to lose heat to surroundings, so you can use some pretty fancy equipment and make sure you lose less heat to surroundings, but you know, as you'll find when we do the experiment in class, we lose a massive amount. Over half of the heat produced goes to the surroundings. So in industry they can get that down to you know, 1% or less of heat being lost to surroundings, so we need to consider that as well. So they are the two main problems that are consistent with all types of calorimetry, but there are also some problems that apply just to flammable liquid calorimetry. So that's, for example, when you're going to be burning a fuel and heating up a liquid. And so when you're burning a fuel, inevitably, not all of the combustion is going to be absolutely 100% complete, i.e. giving you water and carbon dioxide. So you're going to get some incomplete combustion, maybe giving you some carbon monoxide, or even some carbon, or even some volatile organic compounds coming off. So that's the first one, and the second one is by nature they are volatile, and so you're going to lose some to evaporation. So some of the mass that you measure has been used won't have been burnt, it might have evaporated. All right, so you want all of it to, all of the change in mass of the fuel, you want that all to have been burnt for a good reading. But that's not going to be the case. You're not going to burn all of the fuel that is used. Some of that fuel is going to evaporate before you can burn it. So that's another problem applying to just flammable liquid calorimetry. So if you can remember those four, and perhaps also remember a little mechanism to limit those four problems, then you'll set yourself up well to answer those exam questions on that practical. And so lastly, let's check off our learning objectives. Make sure we've set ourselves up okay. So we wanted to know how to measure enthalpy changes, right? So we looked at a couple of pieces of kit to do the experiments with, and you'll be using that type of equipment in the lab for your required practical. So we've been through the first learning objective. Second one was to familiarise ourselves with Q equals mc delta T to work out the amount of heat that was given off or taken in a particular reaction. And we used that Q from Q equals mc delta T in calculations to work out what the molar enthalpy change is for a reaction. And of course we used delta H equals Q over N to get from the Q in the second learning objective to the molar enthalpy change, which would be the final objective. So I think we've clearly been through all three of those learning objectives. So hopefully you've understood. If not, review the presentation again or ask me in class. See you in the next video lesson.